An object with mass 1 kilogram is tied to a string and is doing circular motion with a radius of 8 meters on a smooth table at a speed of 5 meters per second, as shown below. The string is now pulled in until the radius becomes 6 meters. What is the new tension force in the string, and how much work is done by the force? So, we can start by drawing a sort of free body diagram for this object. So, of course, we have the normal force and gravity, the force of gravity acting on it, since it is sitting on a smooth table. And when the table is smooth, it means that there is no friction, so we don't have to account for any frictional forces. And then, of course, we have the tension force keeping it in circular motion. And our coordinate system is going to look something like this. We have the radial direction here. We're going to have the tangential direction here. And of course, we're going to have the direction perpendicular to the plane, which is the direction that the normal force and the force of gravity act in. So we can use Newton's second law, which says that the net force is equal to the mass times the acceleration of the object. So in this case, we really only need the radial direction. So if we wanted to, we can calculate the tension in the string, and I call this T1, which is the tension in the first case. And that is going to be equal to the mass times the acceleration, where the acceleration is the centripetal or radial acceleration, keeping the mass in circular motion. And the centripetal or radial acceleration is also given by mv squared over r. And I'm using subscripts because this is the first case. And if we plug in our numbers, this becomes 1 times 5 meters per second squared divided by the radius of 8 meters. This gives you 3.125 newtons for the tension force in case 1. But this isn't really what we need. So I can write this down. Oops, write this down here. Tension. So if I erase this, the tension force in the first case is equal to 3.125 newtons. But we actually don't really need to calculate this. I'm just calculating this just as an example here, since we can use the same application for the second. Similarly, the T2, tension in the second case when the string is pulled in, is equal to mv squared over r. And in this case, everything is the radius of the new case and the velocity of the new case. And this is simply equal to v2 squared over r2, because the mass equals 1, so 1 times anything is still itself, so we can get rid of that. And we need to figure out what v2 is. So we can do that using angular momentum conservation. So the conservation of angular momentum says that the initial angular momentum of an isolated system is equal to the final angular momentum of it, if there are no other forces acting on it. This is very similar to the conservation of linear momentum, which says that the initial momentum is equal to the final momentum. And it's basically saying the same thing here. And the angular momentum is defined as the cross product between the radius and the linear momentum. And the cross product is given by, so the angular momentum, the cross product of this is given by the radius times the linear momentum times the sine of theta, where theta is the angle between the two vectors. This is simply how the cross product is defined. This can be further simplified to rmv sine theta. And this is because the linear momentum is given by the mass times the velocity of the object. So that gives us the expression for the angular momentum, but we don't know the angle theta, so let's figure that out. So suppose this is the top view of the table, and here we have the string and it's attached, and here's the mass, and it's undergoing circular motion. So this is going to be the radius vector. So this is going to be the radius. And let's say that it's moving down here. It doesn't matter which way it's moving. I'm just going to move it down because there's more room to write here. But it could be going either way. So let's say it's moving down. In that case, its linear momentum will be tangential to the circle because it's the product of the mass times the velocity, where the mass is a scalar and the velocity is a vector. So the linear momentum will be pointing in the same direction as the tangential velocity. So it's going to be tangent to the radius, which means that there is a 90-degree angle between them. And this theta, the angle between the two vectors, is 90 degrees. So this becomes RMV times the sine of 90 degrees. And the sine of 90 degrees simply equal to 1. So this is simply equal to RMV. And this is only for circular motion. In other sorts of motions like ellipses, this would become slightly more complicated. But since our object is undergoing circular motion, we only need to use RMV. So in this case, let me write this. This case, our angular momentum is given by radius times the mass times the velocity. And this is the equation for angular momentum in circular motion. So we can substitute this, we can plug this back into the conservation of angular momentum to get that the initial angular momentum, or the initial radius, times the mass times the initial velocity is equal to the final angular momentum, which is the final radius times the mass times the final velocity. The masses cancel, and solving for v2, or the final velocity, we get that the final velocity v2 is equal to the initial radius times the initial velocity divided by the final radius, which all of this is given in the problem. So the initial radius is 8 meters. 8 meters. Initial velocity is 5 meters per second, and we're going to divide that by the new radius of 6 meters. And this should give you about 6.67 meters per second, or 20 over 3 meters per second. I'm just going to use this one for now. So we can use this to get rid of this. So the new velocity is 6.67 meters per second. And write this up to go. These are the ones that we have solved for, but we don't actually need in the answer. So we can plug that back into here to get v2 squared, which is 6.67 meters per second, divided by the new radius of 6 meters. And this will give us the tension of about 7.4 newtons. So the new tension is going to be equal to 7.4 newtons. So T2, new tension, the final tension, is equal to about 7.4 newtons. And this is almost twice, a little more than twice, the initial tension in the string. But the second part of the question asks us to figure out the work that is done by this tension, by the change in this tension force. So we know from the work energy theorem that the work is equal to the change in kinetic energy. And this is equal to 1/2 mvf squared, or the final kinetic energy minus the initial kinetic energy. This can be factored out to give us 1/2 m times the final velocity squared minus the initial velocity squared. And in our case, we can apply this, 1/2 times the mass. And in this case, our final velocity is v2. That's the final velocity. minus the initial velocity of v1 squared. And we already have everything in here, so we can go ahead and plug in our values. So this becomes 1/2 times 1 times v2 squared, the value that we calculated, minus v1 squared, which is given in the problem. And this will give you about 9.7 joules. So, in addition to the tension force that we're supposed to calculate, the work is equal to 9.7 joules. And that is how you would solve this problem here.